Our next speaker is David Wärn, and he will tell us how to get the naturals from the integers.
Yeah, that's right. Okay, so yeah, and this is joint work with Christian. So let me first say what I mean by constructing the naturals from the integers. So I think we're all familiar with the universal property of the naturals. So they are a type freely generated by an element 0, a self-map successor. So I take this as shorthand for like the induction principle for the naturals that you see in the output. Okay, so if this is the naturals or the integers enjoy a similar universal property. So they are freely generated now by an element 0 and a self-equivalence successor. So again, this is shorthand for something more complicated, an induction principle, which says that if you have some motifs or a type family over Z that you want to prove, you have to prove it over 0, and you have to do this inductive step, where now this has to be an equivalence. So the inductive step has to be reversible. And then the conclusion is the same as for not induction. You get a section of P with the same equations. Right, okay, so now that I've said what NAT and Z are, so this is our result. So we work in a kind of minimal type theory with only these basic principles. So we have a unit type, sigma, identity, function type with function functionality, and a Boolean type with the large elimination. So I don't include a universe here, but if I had a universe, then large elimination would be automatic. It's just the fact that you can define a type family over the Booleans by this system. And so the combination of sigma and Booleans gives me binary coproducts. So this is what I would like to use. So this is the setting, and then the result is that if you have Z, you can construct N. So if I wanted to be more precise, I would say that if I have a type with the universal property of Z, I define the type with the universal property of N. Yeah, and we have two proofs of this, and so I will present one of them in this talk. But so now you might be wondering, I mean, this seems kind of backwards. So usually you think of N as primitive and Z as something that you define from N. So why would I be looking at this weird converse result? So yeah, we put differently, where does Z come from? So the motivation is that, so if you have moreover a circle type freely generated by a point of the self loop, and you assume it has a large elimination, which you always do in HoTT, then you can prove that the loop space of the circle is freely generated by reflexivity and post-composition by loop. So I mean, this is not a new result, this is kind of folklore. I guess it appears in this paper by Carlson Rammer. And I think it's been attributed to Paolo Capiotto. And another way of stating this result is that omega S1 is. So I mean, but when I write this, I mean something a bit different from what you usually mean. So the point is that this works regardless of whether you have beforehand a model of Z. So S1 gives you Z, even if you don't have it. So I mean, the question then is, okay, it gives you Z, but does it also give you M? It would be like the infinite type you're actually interested in. And maybe I would say, so S1 is also kind of like a reasonable type in the sense that it's a non-recursive hit. So just looking at the description of S1, you wouldn't expect that it gives you anything infinite. Because that's what happens in, I mean, without hits. Right, so let me say what's been done before. So as far as I know, this question was first discussed by Egbert Reich and Mike Schulman in the N forum. And they noticed that you can construct naturals from the integers if you also have an impredictive type of propositions, so with propositional resizing and a universe. And then later this was improved by Robert Rose in his PhD thesis, to show that actually you can do without impredictivity, which was kind of surprising because, so you should think of impredictivity as a source of inductive definitions. And it seemed essential in this argument, but Rose gave an argument which avoids it, but uses instead a univalent universe. And then so Nima Rasek has also written about this in the context of higher category theory. where he assumes also sort of sub-object classifier, which is like this impredictive type of propositions. So let me say, so these have both been formalized actually in POC and yeah, so yeah, now I would say, what is the idea behind our proof, or one of the proofs? So to start with, let's think about how to relate the naturals and the integers. And for this, let us first suppose that you have the naturals. So how would you understand integers? What you do is you observe that, so 1 plus n is equivalent to n by including 0 and the successive n to n. And then given this equivalence, you can construct this more complicated equivalence on this type n plus 1 plus n. So this is what you expect the integer to do. And what is the self-equivalence of this type? Basically, you can define it in terms of this. So it sort of reassociates. And then what is this equivalence? It kind of does this in reverse here from n to n plus 1, and then 1 plus n to n. So it sort of shifts things to the right. Okay, so this is a self-equivalence of a type, and you also have an element in the middle here. So by integer reduction, you get a map from the integers. Yeah, and I mean, you can think of it as characterizing negative, 0, and positive integers. And what's surprising is that, I mean, you cannot define this directly with integer reduction. You kind of need some intermediate thing. Okay, but in our setting, we don't have the naturals. So what do we do instead? So the same thing works whenever you have two types, A and B, with an equivalence A plus B to B, and a point of A. There was nothing special about 1 and n in the previous step. So how do I instantiate this then? Well, you prove that Z plus Z, I mean, that's kind of the only type you have available. So you prove that Z plus Z is equivalent to Z. And this is kind of direct. So by so doubling and halving. So if you go from left to right, it's doubling, and going right to left is kind of a division by 2 operation. But the point is that it's direct to prove just using integer induction. You don't need anything else. Right, so given this map, we obtain a map Z to Z plus Z by, as before, by integer induction. And then, so you can compose with the map Z plus Z plus Z to 1 plus 1 plus 1 to get a sign map. So it's saying that there's kind of 3 kinds of integers. So we get a decomposition of the integers into 3 parts. So a negative, 0, and positive. And this one you would expect to be contractible, but it's not so clear directly. And then the important property of this decomposition is that, well, one is that Z lies in this, 0 lies in this part, and a successor of X is sort of lies in the positive part if and only if X is either 0 or positive. Right, okay, so we have this decomposition now of Z, and you would expect that the naturals are just the positive part plus the 0 part. We will not show this directly. Instead, we will construct the naturals as a sigma type over this thing. So we have to do 2 things. We have to actually say what is the sigma type, and then we have to prove the validity of this integer reduction principle. And for both parts, we use essentially the same idea. So this is the idea of thinking about, so I write partially defined inductive functions. And this is the same idea as, like in set theory, if you want to prove a recursion principle from something weaker, an induction principle, where you only prove properties. You sort of structure the goal to show that up to any point you have this partially defined, a unique partially defined inductive function. Okay, but so for this, you first need a way to compare integers. You want to talk about finite the prefixes of the integers, or of M. So first we define subtraction as a binary operation on Z, and this is direct by integer induction. And then given subtraction, you can define this so decidable ordering x is less or equal to y to mean that x minus y is either 0 or negative. And I write some basic properties of this ordering that you can prove directly. And then, of course, I mean, we expect to have more properties, like we expect to have transitivity, but it's not so clear how to prove it, and we won't use it. So, right. Okay. So, what does this have to do with inductive function? So, when I say inductive function, I mean, I suppose you have a type family over M, and you have this data, which is like what you would need in order to define a section of A by induction. But here I wrote something a bit stronger than just A of 0. I write that you have A whenever A of x whenever x lies in the 0 part. Okay, so given this data, you can think of we define this type of BU as so partial functions defined up to U. So that you have AX whenever AX is at most U. And then you can define these maps, which I call restriction and extension. The restriction is kind of direct. If you have defined something up to SU, then in particular it's defined up to U. And extension is a bit more complicated. So if you have something defined up to U, you can extend it to something defined up to SU using basically these assumptions and a case distinction on M, which again, the M is co-product. So I introduce these things because now I can economically say what it means for a function to be inductive. So, I mean, inductive should mean that it satisfies this defining property of a inductive function whenever the recursive equations make sense. But the efficient way of expressing this is just that f equals the restriction of its extension. And I will write I of u for the sigma type of the functions that are in it. So the reason this description was useful is that we have a nice lemma about this kind of type. So there's a type of error, but I should have f from x to x. I define the type of fixed points of f as what you expect. So elements with a proof that it is fixed. And then the key lemma, which I call the rolling rule, is that whenever you have maps back and forth between x and y, the type of fixed points of the two composites are equivalent. So if you see this lemma, you might think, okay, it's going to be some ugly path algebra because the type involves some path component, and yeah, you have to prove some path algebra when defining the equivalences back and forth. But what was really nice was that there is a super direct proof of this, where instead of defining an equivalence between these two types directly, you produce a third type, which is equivalent to both. And now you can kind of see directly why this is equivalent to either one, because you can contract away on this pair, and you are just left with one type, or you can contract away on these two pairs. Right, okay, so that's the rolling rule, and so the point is that you can use it to characterize these types of inductive functions. So one thing which is kind of direct is that a inductive function defined up to 0 is just, there's a unique one, it's like a 0A. So it's this type of fixed point of a constant map. And then to understand inductive functions defined up to SU, the point is that they're the same as inductive functions up to U. So you kind of have no choice when you want to extend an inductive function. And so this proof uses crucially the rolling rule from the previous slide in this step. We use the two. First, there's an operation that restriction and extension can commute in some sense. So this line is indirect, and then this is using the rolling rule. Right, so now I can say, how do we actually define the naturals? So the idea is to instantiate the A from before using M itself with a sort of perturbed structure. So instead of 0A, which should go from Z0 to A, or Z0 to M, You could think of this as, well, you would take like the usual inclusion, but instead I take it to be constantly 0 to kind of rectify. I mean, you can imagine that M contains possibly some non-standard numbers that we're not interested in. And for N, we want to use only the standard ones. So that's the point of this. And then, so I define again the naturals as a sigma type over M. So I define this type M of M, which kind of expresses that M is like a standard form for a number. To mean that I have a inductive function defined up to M, which takes the value M at M. Right. And then the crucial property of this is that so we didn't know that Z0 was contractible, but what you can prove is that when you sigma with M, it becomes contractible. And that you have this equivalence. So M is standard if number, SM is standard actually. Yeah, and then there's a derivation of N induction, which is also, so I express the motif in this way of the natural number induction, this N is sigma type. And then you kind of instantiate A again with this data. And instead of proving that directly you have a section of P, what you prove is that you have inductive functions for the N by Z induction. Then it's direct that you have the desired conclusion. So section of M compatible with successful. Yeah, that's what I have to say. So thanks for your attention. Yes.
At the beginning, you mentioned you have 2 proofs.
Yeah.
Can you comment on the second one?
Oh yeah, I forgot to mention this. So the second one is what I would say. This one uses more kind of new kind of ad hoc ideas, and the second one is maybe more. Yeah, it uses different ideas that are, I would say, closer to what Robert Rose did in his thesis. So Robert Rose has quite a complicated construction, which also uses the universe, and then our second proof is somewhat similar to this, but much simpler, and we eliminate the use of the universe by a trick. So, yeah.
I'm just wondering, so what exactly is the power? I mean, you have this type theory like with S1 and the usual equipment, and you get already arithmetic out of it. Is it clear that you don't get anything more than arithmetic, or can we have a model of this type theory using arithmetic?
Yeah, it's a good question. I don't know. So
sorry, I mean, I didn't expect you.
Yeah, I'm not sure. So I would say one thing you don't get is universes. So,
but I mean, I guess you don't get infinitely branching types, but is this clear?
Yeah. So, for example, in our system, you couldn't define a type family over N by that. It doesn't give you too much.
Yeah.
I don't know.
But I mean, I think what I'm really saying raises this question. There's this basic type theory, which is not finite in a sense, but it has already power of arithmetic. But maybe then it means it's actually something which is more or less equivalent to arithmetic.
Yeah, it could be. I don't know, but yeah, I mean, it's a bit difficult to find models, so it's.
More questions? In the case, then let's think about it again.